Hi, welcome to my 3SH3 project. The topic I'm doing is deadlock. So let's begin. What is a deadlock? Deadlock is defined as a permanent blocking of a set of processes that compete for a system's resource. Deadlock occurs when a set of processes are blocked because each process is holding a resource and waiting for another resource, which is being held by some other process. Hence, all deadlocks need two or more processes. So what this slide is saying is that when a deadlock happens, it's permanent, and deadlock happens when two or more processes are competing for the same system resource, and a deadlock occurs when a certain set of conditions are met. So here's a real life example of deadlock. So here we have a bridge. It's a single lane and one-way bridge, and then the cars can be considered as processes. So when the yellow and red car both come onto the bridge in opposite directions at the same time, they get blocked, so a deadlock has occurred. And you can note that if this red car had not come, then there would have been no deadlock. So a specific condition had to be met for the deadlock to occur. Conditions for deadlock. Uh, the four conditions for deadlock. First one is mutual exclusion. Only one process can use a resource at a time. Hold and wait. A process is holding at least one resource and can request new resources. No preemption. A resource cannot be taken from a process unless the process releases the resource. Circular wait. A set of processes are waiting for each other in circular form. To further explain, the first three of these processes are not sufficient for a deadlock, but are required for a deadlock. So that means that if we have these three first conditions, a deadlock may happen or may not happen. But if we have circular wait, deadlock will always happen. To further explain deadlocks, we can use this simple deadlock example. And here we have four processes and four resources. Process 1 is holding process resource 1 down. Process 2 is holding resource 2. Process 3 is holding resource 3. Process 4 is holding resource 4. And then process 1 wants resource 2, so it has requested for resource 2. But then it sees that resource 2 is already using by another process, so it is waiting for resource 2. Same with resource 3 and resource 4. And process 4 is waiting for resource 1. So how does this fulfill these four conditions? So mutual exclusion says that only one resource can be used by one process at one instance of time. So here, since resource 2 is being used by process 2, process 1 cannot access it, so it's waiting for it. The other one is hold and wait. So a process can hold at least one resource and also request for new resources. So process 1 is holding resource 1 and is requesting for another resource, which is resource 2. No preemption, which means that when a process is working on one resource, another process cannot take it from it. So since process 2 is working on resource 2, process 1 cannot take resource 2 from process 2. So process 1 ends up waiting for it. And circular wait. So you can see here that when process 4 wants resource 1, but process 1 is already using resource 1, so it has to wait. And in the end, we end up with this circular form, and all of the processes are going to end up waiting for the other process, and they're going to so this is a deadlock, and it's going to they're going to be in the state for like infinity or for infinity. So how do we handle a deadlock? There are three ways to handle a deadlock, which is detect a deadlock. Once a deadlock has occurred, try to detect and take action to recover. Avoid deadlock, carefully allocate resources, check if granting the resource will cause a deadlock. If yes, then don't grant it, and prevent a deadlock. So implement an operating system that does not follow one of the four conditions which cause a deadlock. So these are the four conditions we're talking about. So preventing a deadlock means that we implement an operating system in such a way that the possibility of deadlock is zero null. So the two methods to do this, the direct and indirect method. In the direct method, we try to prevent circular wait. So we try to implement the processes in such a way that circular wait does not happen. And the indirect method is simply trying to prevent mutual exclusion, no preemption, and or hold and wait. To avoid a deadlock, we carefully allocate resources, check if granting the resource will cause a deadlock. If yes, then don't grant it. The two methods to avoid deadlock: process initialization denial. So if starting a process can lead to a deadlock, then we do not start it. And resource allocation denial, which means that don't grant resources to a process if the resource allocation might lead to a deadlock. So what does resource allocation denial mean? That is that we allow the process to start and take some initial resources, but when the process requests the system for more resources, uh, we check if granting that resource will cause a deadlock. If yes, then we don't grant the resource, and this can be implemented using Banker's algorithm. And as we're going to be short on time, I'm gonna go more into detail on Banker's algorithm. So and so and might have missed some points related to process initialization denial and how to detect deadlock. But since my topic, the question I'm doing is more related on Banker's algorithm, so the rest of the slides are going to be related to Banker's algorithm. So in Banker's algorithm is a deadlock avoidance algorithm. It analyzes the current allocated resources and the resources required in the future, then tells system if it will go into deadlock or not. So there's a safe and unsafe state. So if even one process can occur, so that means it's safe. But if none of the processes can occur, that means it's unsafe state. How does Banker's algorithm work? So basically, Banker's algorithm can be implemented using four arrays. The first one is available array, which represents the total number of current available resources of each type. Max resource, which represents the maximum number of instances of each resource that a process can request. So, which means that the total number of resources available in the system in the start. The allocation array represents the number of resources allocated to each process, and claim represents the remaining resources required by each process. So here's a diagram of Banker's algorithms matrices. So this is our claim matrix. So here we have processes and here we have resources, and each process requires a specific amount of each resource to complete. And then here we have the allocation matrix, which shows initially how many resources each process is holding. So, and then we have this array, which is simply subtracting the claim minus allocation matrix. So, for example, since process 1 requires three resources of type 1, and initially we already have one resource being held down by the process, so we need two more. And similarly we fill in the other one. So 2 minus 0 is 2, 4 minus 2 is 2, 1 minus 1 is 0, and then that's how we fill the rest of these boxes. So, and the max resource matrix is basically the total number of resources available in the system in the start, and the available resource matrix is the total number of resources currently available. And how do we calculate this? Is basically we first calculate how many resources of each type are being used by system by the processes. So here are there 4 resources of R1 being used. We had 6 available. 6 minus 4 is 2. Same with R2. We have 1 available. So 3 minus we have 3 available and 1 is being used. So 3 minus 1 is 2. Same here. 5 minus 3 is 2. 3 minus 2 is 1. After setting this up, then what we have to do is check each process and see if it's safe or unsafe. So if we look at process 3, it requires 4 of resources of type of R1, but only 2 are available, so this is unsafe. Process 2, we have it requires 3 resources of R1, but we only have 2 available, so that's unsafe. But process 1 requires 2 and we have 2 available, so that's gonna work. So same with R2, it's gonna work. R3, we have 2 required and 2 available, it's gonna work. And R4 requires 0, so P1 is safe, it's gonna run. So after our P1 runs, we'll be able to free up these resources, and this is going to be added to our available resource matrix. So 1 plus 2 is going to become 3, and then 0 plus 2 is going to stay as 2. And for R3, 2 plus 2 is going to become 4, and R4, 1 plus 1 is going to become 2. So that's what we did over here. So after P1 runs, this is going to be our new available resource matrix. Now we can see that P2 can also run, since R1 and the 3 are available and 3 are required, and for R3, 2 are required and 4 are available. And then after this runs, then we can check if P3 runs. So that means this is safe. And this is basically the concept behind Banker's algorithm. Now let's do a textbook example. So In this question, it says consider a system with a total of 150 units of memory allocated to three processes as shown below. So here is shown. And then it says apply the banker's algorithm to determine whether it would be safe to grant each of the following requests. If yes, indicate a sequence of terminations that could be granted possible. If no, show the reduction of the resulting allocation table. So first, let's set up this table according to banker's algorithm. So we have three processes, and initially they require in total they require process one requires 70 resources, process two 60, process three 60, and initially they're holding 45, 40, and 15. So that's how we set up our claim and allocation metrics. And then we can subtract our claim and allocation to find how many more resources of each type each process requires to complete. And then in the question it told us that the system had a maximum resource limit of 150. And then we can add 45, 40, and 15 and subtract it from 150 to find what the current available resources are available in the matrix. So this is like the initial state. Okay, and we can see that process 1, 2, and 3 can all run since the currently required is less than what's available. So this is safe. So now if we go into the part A of the question, it says that a fourth process has arrived with a maximum memory need of 60 and initial need of 25. So now it says that a fourth process has arrived with which requires 60 units of memory. Initially it has 25 allocated. So and if you minus 60 minus 25, we find that it will require 35 more memory to run. And now since we have four processes, our total available resource matrix value is also going to change. So 150 minus the summation of these four processes equals 25. Now we need to check if we have a safe state. If we check process 4, we see that it requires 35 and we only have 25 available, so that's unsafe. If we check process 3, we see it requires 45 and we only have 25 available, that's unsafe. But if you look at process 1 and 2, both of them are safe since we have the available resources required to fulfill them. So now we can either go with run process 1 first or process 2 first. So I'm going to be running process 1 first. So if process 1 runs, we will be able to free up this 45 units of memory, and this is going to become 0 and this is going to become 0, and 45 is going to be added to 25 over here. So this is what we end up with. And now we can see that now we can run the next process, and we see that process 2, 3, or 4 can all run. So the system isn't safe and no deadlock will occur. So what about part B of the question? Now in part B it says, what if a fourth process arrives with a maximum memory need of 60 and initial need of 35 units? So if the fourth process arrives, it has 60 required and initialize is 35 units. So 60 minus 35, it'll need 25 more units of memory. But due to this number changing, our available resource matrix is also going to change. So after adding summing all of these resources and subtracting from 150, we see that our current available metrics R1 is only 15. And now we see that none of our processes will be able to run since 15 and the current available resources is 15, and all of the processes require way more resources than that's available. So if we allow any of these processes to run, the system is going to go into an unsafe state and a deadlock will occur. So this is the end of my presentation. Thank you for watching it.